Today we're starting a unit on uniform circular motion. In this video, we're going to be learning the terms centripetal acceleration and centripetal force. And what I want you to get out of this video is the fact that when an object is moving with uniform circular motion in a circle with a constant speed, the acceleration and the force on that object are directed toward the center of the circle. That's what centripetal means. It means center seeking. So what are some things that move with uniform circular motion? What can you think of? One thing that I think of is the moon. It more or less moves in a circle with uniform speed around the Earth. Another thing is an electron. In the Bohr model of the atom, electrons move in a circle with uniform speed around the nucleus. Something we're going to be looking at in a lab in class is an eraser that you're going to twirl over the top of your head. This is an eraser tied to a string. The string goes through a plastic tube, and at the other end of the string is a weight. And I can twirl this over the top of my head, and the eraser is moving in a circle at a constant speed. So this is uniform circular motion. In the lab, we're going to be looking at the relationship between the speed and the acceleration of the eraser. But during this video, I want to do some analysis of circular motion to see what we can find out about the direction of the acceleration and the direction of the force on an object. So let's say this is the circle that the eraser is moving in. At a certain point in time, the eraser is right here. Let's say it's moving in this direction. I'll draw the velocity vector in blue. There's velocity. And we know from Newton's first law of motion that an object in motion tends to stay in motion in a straight line at a constant speed. So if there was no force on the eraser, it would move in a straight line at a constant speed. But it's not moving in a straight line, it's moving in a circle. So there must be some kind of a force on that eraser. And one way to think about this is, let's say that sometime later, the eraser is here, and at this time, the direction of the velocity is in that direction. It's the same length, the same magnitude as it was before, but the direction has changed. So what needs to happen to make this eraser get off the path that it should have been on if there was no force? It should have been gone like that, but it's here now. So there must be some kind of a force in this direction to pull it off that path. And again, a little bit later, the eraser is over here. Same thing. It would have been along this path, but something has pulled it over to this point. It must be a force in this direction. So we can see from this quick and dirty analysis that the direction of the force is toward the center of the circle. I want to do a little bit different analysis, a little more rigorous analysis with vectors. So I'm going to say that this vector, this velocity vector, is our initial velocity, v sub I. And this vector is our final velocity, v sub f. If I move this vector tail to tail with this one, the same direction, the same length. We have that. And I want to find the delta v vector, the change in velocity. We know from our previous studies that delta v equals final velocity minus initial velocity. And we know that when we're doing arithmetic with vector quantities, we can do the same thing we do in algebra. I'm going to add vi to both sides. And here we get delta v plus vi equals, these cancel, v sub f. Delta v plus vi equals v sub f. When we're adding vectors, we add vectors head to tail, and we get a resultant vector. So looking at this diagram, where do I need to put delta v so that I have delta v plus vi gives us a resultant vector of vf? It's right here. I have vi added head to tail with delta v, and the resultant is vf. So this vector analysis shows us that our delta v is, again, toward the center of the circle. We know that acceleration is delta v over delta t, where acceleration is a vector, delta v is a vector, delta t is a scalar. So delta v must be in the same direction as the acceleration. So we've got an acceleration vector that must also be in this same direction. And we know from Newton's second law F equals ma. Force is a vector, acceleration is a vector, mass is a scalar. So the acceleration and the force must also be in the same direction. So there must be a force directed toward the center of the circle. Force directed toward the center of the circle is called centripetal force. Force, an acceleration directed toward the center of the circle is a centripetal acceleration. One last thing I want to close with is that when we're talking about centripetal acceleration is not some new kind of acceleration. Centripetal force is not some new kind of force. It's just, in terms of centripetal force, it's just the net force acting on an object. And if the object is moving in a circle, that net force must be directed toward the center of the circle. So in the case of the eraser, the string is providing the centripetal force. In the case of a race car driving in a circle around a circular track, the centripetal force is provided by the friction between the wheels and the pavement. In the case of the moon orbiting the Earth, it's the gravitational force from the Earth that's providing the net force that is the centripetal force. So centripetal force is not a new kind of force. It's just the net force that is causing an acceleration like we've seen in our past studies. All right, that's it. I'll see you in class and we'll work on the lab.